SwayamPrabha. Digital India. Educated India.
So we were looking at the Z transpose T Z. So that Z transpose T Z, or the Z is an important thing, important quantity in inverse problems. Of course, it's an important problem in solving optimization problems also, because eventually we are solving an optimization problem. Actually, we are minimizing something. Okay, in this case, what is that minimizing? We are minimizing the sum of the squares of the residues. Sigma Ri square I equal to 1 to n. That's called S. Okay, so the Jacobian, the general notation for Jacobian mathematicians uses J. Okay, so we started with some Z. Okay, so that's okay. Z and J are one and the same. So there are several ways of calculating the Jacobian. In our problem, we had a very simple form for the y itself, for theta equal to a into 1 minus e to the power of minus bt. So in which case the components of Z were very easy to figure out. Okay, so that you're able to calculate the various elements of the Jacobian. For example, if the problem is difficult, how do we go about calculating the Z or J? That is the subject matter of today's lecture. Okay, a direct analytical formula is possible. That's what you have done. Okay, dou theta by dou A equal to 1 minus e to the power of minus bt. Then so you substitute t equal to t1, t equal to t2, t equal to t3, blah blah blah. But the problem is it requires a knowledge of B, and B is what you want to get in the inverse problem. Therefore, you assume a prior value of B and put it. So the Z itself depends on the initial condition. That is why it is a nonlinear regression. I repeat again and again and again and again. I'm saying this. Okay, at least when I say it 4 or 5 times, somebody has missed sometime. All of you will catch at least once. Okay, that is the idea of a teacher repeating. Okay, it's not that we have nothing else to teach. Basically, we reiterate so that even if you have missed, okay, at least once you will pick it up. All right. So you can calculate with direct analytical formula. That's what we did in our class. Or you can always also do it by finite difference method if an analytical evaluation, the Jacobian, becomes very difficult. Or you can actually construct and solve what is called the sensitivity problem. That is, you will construct a sensitivity problem and solve it either analytically or numerically. So for a very simple case, I will demonstrate this in today's class. Okay. So today I will be going a little fast. I will not be giving you time to do work yourself. It will be a little fast. It will be a little compressed lecture because I want to cover good ground today. But if there's any problem, you stop me in between. You just say something is not clear. All right. Then I'm ready to explain it. Okay. But I'm not giving time to you to solve. Okay. Except maybe when we come to this. All right. Now, the Jij, okay, equal to dou Ti by dou Pj, for example. Okay. So let's say temperature is a function of parameter. P is usually used for parameter. That parameter can be thermal conductivity, density, specific heat, emissivity, or whatever. Okay, in this case, it could be the time constant, A, B, whatever. The parameter is generally denoted as P. Temperature is T. Okay, so the Z is actually, so you know that. So dou T1 by dou P1, dou Tn by dou P1. Okay, dou T1 by dou P2, dou Tn by dou P2. Okay. No, let's make it R. Okay, so dou Tn. We always had N. Okay, we always had N. We had N measurements and R parameters, whatever. Okay, this is the Jacobian matrix. Okay, so R parameters. And data points. What is the goal? The goal is to fill the matrix. Only with this, you will do Z transpose Z, blah, 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 all that. Okay. And you can do plus lambda I, Tikhonov, Marquardt, Alifonov regularization, Tikhonov regularization, whatever you want to do. First, you should be able to calculate the Z or the J. If you're not able to calculate the j, we cannot proceed further. Okay. So in order to solve the inverse problem using a calculus technique, we require j. Sometimes, just for the sake of studying the physics of the problem, I want to calculate the j. I want to know at which places, okay, at which places in the domain, or at which points in the time domain is the temperature sensitive to some parameter, okay, p of 2 or p of 3, which I want to study. Are you getting the point? Okay. Suppose I have a problem with money, I have a problem with time, I have to do the experiment. Then if I have only limited resources and time available, should I do the experiment at 1000 time steps, 1000 time instances, or I can do it with only 20 time instances? Suppose temperature is a function of x, y, z and time. At how many different places in the medium, at what all time instance will I measure the temperature? Okay, so that I get a meaningful solution to the parameters which cause that. That is my inverse problem. So first I have to study the getting drowned in mathematics is one thing. You can solve this thing, you can do a method of separation, whatever. That is okay. Mathematics, that's okay. But let's be engineers. So we have to find out where are the places, which are the parameters which affect the temperature significantly. Therefore, I will put my thermocouple. I will do my measurement only in those places. I will do my measurement only at those places, at those time instances, whatever you want to call. Therefore, solution is only one part. Understanding the physics so that you become a better engineer is afforded by things like a Jacobian analysis. Even if eventually you do some high funda maths to solve the problem. So where you will put the thermocouple is something which the engineer has to decide. You are the analyst. Finally, it is a heat transfer problem. Mathematics comes only in between. Mathematics comes in between and goes out. What originally remains is there is a system which is getting heated. I want to cool it. I want to blah, blah, blah. Because ultimately we are studying a heat transfer system. Therefore, getting the elements of this is very critical. Not only for the solution to the inverse problem, just to study the problem so that I'm able to do what is called a better inverse design. What is a better inverse design? So for example, this could be a furnace, and then these temperatures are various points in the furnace. Suppose I want to design the furnace such that the deviation in the temperatures, okay, at various points in the furnace is less than a particular minimum. Then you have to study the Jacobian. More than the inverse problem, you have to study the Jacobian. You have to find out what is happening. Then you have to go and maybe put some holes, maybe put some fan, you redesign the shape. Then you will start doing actual engineering. Is that okay? All right. Now, this is as far as the preamble is concerned. Okay. Now, take down this problem. Problem number. What will be the problem number? Anybody? Arvind, Raghav, Ameya,
12,
somebody?
sir.
Huh?
12.
13.
Hey, every day you're saying 12 month end. So we have to progress in life. 13. Okay.
No, sir.
Okay. 13. Okay. So consider the unsteady problem. Unsteady conduction problem. Equal to rho Cp by delta. 0 less than equal to x. So this is basically a slab. Okay, some slab like this. So it's a slab. Okay. So here you're giving Q0. And it is getting heated. Now you want to. So this problem concerns the story of the slab. What story? The story of the temperature of the slab. What is the story of the temperature of the slab? Temperature is a function of x and t time. So I want to understand it. Okay. So that is a fault. So this is called the forward problem. Okay. Boundary conditions minus k dt by dx dou t by dou x equal to q naught, x equal to 0 and time greater than 0. Okay, this is equation 1. This is equation 2. then I'm actually insulating the other side. So T by T, so that I don't allow a steady state solution for the problem. But I said something very poignant in passing. I don't know how many caught my what I said. Huh? I don't want to repeat. If you are very keen, you would have noticed it. Otherwise, watch it in the recording. Huh? Just 30 seconds back, I said something very casually, but that's very deep. Huh? Okay. So, or somebody wants to recollect, somebody wants to say what I meant. Does anybody remember what I said a minute ago?
The other side of the slab is insulated so as to prevent a steady state from occurring.
Ah, exactly. What is the story now? This side is insulated and I'm continuously heating. So the temperature will continuously increase. So there is no steady state solution to the problem. So it is not just the equation which will decide the temperature distribution. Please note it is a boundary condition which can really trouble it. Okay. Now the initial condition will be T equal to Ti for 0 less than equal to n. Okay. So it is dou square T by dou x square. Second order in x. So two boundary conditions in x at x equal to 0, x equal to L. It's first order in time. Of course, if it's second order in time, we are finished. It is hyperbolic heat conduction equation. There is a controversial heat transfer theory. Okay, there is a time lag in the propagation of the heat wave. Let's not get into that. So far, we have not been able to experimentally validate this. So a lot of papers come in our journal. We have a lot of scientific debates. Our journal policy is to reject any paper which reports dou square T by dou T square because the time scales, it requires femtoseconds and all that, and we don't have wherewithal to do experiments to confirm it. Simply, you can publish papers, write some solution, MATLAB code, and publish. And the top journals, we are not going to allow. We are going to reject. Okay. If you do an experiment and show, fine. But we know that they cannot show it. Huh? So they may be upset with us, but any paper with hyperbolic heat conduction, International Journal of Thermal Science, we will reject it. Okay. You might have spent 2 years on that work, doesn't matter. Because if you cannot do it experimentally, we don't accept it. Any amount of theory is no substitute for experiment. Okay. Otherwise, we go to a mathematics journal. Okay. We don't want validation. If you're doing engineering, finally, the idea of studying mathematics is so that you realize something. I mean, ISRO, why is it so much valued? Well, month after month, they say something is going up and it's putting sadly, you're getting pictures, you're watching TV, you're able to do your mobile, all that, because they're able to prove, okay, that they can realize something, make something, put it in a rocket and it can go up, huh? And launch it there, and that fellow will keep on inside 3D. You get beautiful pictures. Just look at IMD website, India Meteorological Department. Okay, all right. Now, the question is like this. Set up the sensitivity problem. Oh, sorry, set up the sensitivity matrix for the above forward problem. Set up the sensitivity matrix for the above. Sorry. Set up the sensitivity matrix for the above 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 forward model with respect to K, with respect to thermal conductivity K. I come again. Set up the sensitivity matrix for the above forward problem with respect to K. So I'm interested in JK tires. Okay, JK is dou T by dou K. So this is the Jacobian. How the temperature varies with thermal conductivity. How the temperature varies with thermal conductivity at different points in the medium at different times. That is the Jacobian matrix. Is that okay? I come again. There is only one parameter. So it is not P1, P2, P3. P is just a single parameter. So that the problem is tractable. You know what we are. So you know my style of teaching is after I teach you a theory, we'll demonstrate with an example so that the learning is reinforced. All right. So let's take a very simple one parameter problem. The temperature is a function only of thermal conductivity. Okay, rho Cp. Let us assume that rho Cp is known. Otherwise, that can also be taken as P1, P2, and all that. Let's not complicate things. Let's keep things simple. Now we want to evaluate this. Okay. Now, solution. I'm sorry that I'm not going to give it any time. I'm going to do it myself. Okay. So K dou square T by dou square. So the question is to get the Jacobian equal to rho Cp dou T by dou phi. Okay, 6. Now I do dou by dou k of this equal to dou by dou k of rho Cp dou T by dou phi. Okay, dou by dou k of dou T by this thing is dou square T dou square T by dou x square plus what is the left hand side?
Plus
Huh?
k into dou 3t by dou k dou x2.
Who is that? Is this okay?
Yes, sir.
Okay. Who was that? Manthan? Subhas?
Yes.
Okay, fine. Okay, so watch the arguments very carefully. Okay, watch the arguments very carefully. So, rho Cp, because you have not done it. I know that you have not learnt it anywhere. Okay. So far in life, you have not learnt it. This is all new to you. So, rho Cp, this thing is basically that will become right side is what? Rho
Dou t of dou t dou k.
Dou by
Dou t.
is that okay, Subhash?
Yes, sir.
Very good. Okay, so dou square t plus k dou t by dou k is basically jk. This is our jk tire. Okay, is basically dou square jk by dou x square equal to rho Cp. Please note that quietly we change the problem into a problem in J. So we are composing a problem, or what is it called? Formulating the problem, not for T now. We are formulating for J. And now you will have a different set of you will have a differential equation with initial and boundary conditions. If you solve, you will not get the temperature, you will get the J. Okay. So this is the sensitivity problem. If you look at any mathematics journal, mathematics book, advanced book, they will say sensitivity problem, sensitivity problem. They'll go one step further. The adjoint problem. The adjoint problem is basic. I will come to that. That's very advanced. We'll come to the adjoint problem in Monday's class. I mean, Monday after this Monday. Okay. So this is done. So this is the equation 7. Okay. Now BCs and IC. Minus k dou t by dou x equal to q naught at x equal to 0 for all times greater than 0. So this is nothing but minus dou by dou k of k dou t by dou x equal to dou by k of that is 0. Okay. So right side is 0. Left side is dou t by dou x minus k okay by dou. So the left side boundary condition becomes like this. Of course, the t is also there. You have to solve for the t also. Unless you have the solution for t, you may not be able to proceed. That doesn't matter now. As far as we are concerned, at this point in time, we are interested only in a formulation for the Jacobian problem. Is that okay? So equation 7. So this is 8, 9, 10 water. Is this clear up to this? Now at x equal to L, t by dou x equal to 0. Therefore, dou jk by dou x equal to 0. well. Okay. Now, initial condition 0 less than equal to x less than equal to L for time t equal to 0, t equal to Ti. Okay. Now take dou by dou k of t equal to jk equal to dou by dou k of Ti. Fortunately, the initial temperature is not a function of the thermal conductivity. Therefore, it is 0. Now, seven, 10, 12, 13. So 7 is a second order equation in JK. So 7 along with the boundary conditions 10 and 11 and the initial condition 13 is the formulation for the sensitivity problem. If you solve it, you'll find out JK. But it may not be so easy to solve it because that T is there. So if you have T, dou T by dou X is also coming. So maybe you first need the solution to the forward problem itself. Regardless, if you crack this problem, whatever means, numerically, analytically, whatever, you'll get a handle on the Jacobian. That means you will get to know how the temperature changes with thermal conductivity at all points in the domain, at every point in the domain, at any time t, which you specify in your consideration 0 is less than equal to t less than equal to some t star, whereas a t star is the time limit of your consideration, and 0 is less than equal to x less than equal to L, where L is the thickness of the slab. So across all time instants, for all time instants under consideration, across all points in the slab, how does the temperature at any point in time and space vary with respect to the parameter of interest of thermal conductivity? That is the sensitivity problem. That involves the Jacobian. This is how we formulate it. You can solve it by any means you want. Any doubts so far? Is that okay? So in multi-dimensional problems, it may be well worth the effort to actually find the Jacobian. If there are too many parameters, the temperature or heat fluxes are a function of too many parameters, I would rather solve the Jacobian and plot the Jacobian J in multiple colors. And then red color means Jacobian is high value. Orange color, Jacobian is medium value. Yellow is slightly lower. Blue is the cold. So this is called a heat map. You can do a heat map of the Jacobian and find out wherever the Jacobian is showing red color, there you will place the thermocouples. If you have got money, if each thermocouple is 500 rupees, you've got only 50,000 rupees, you have to put 100 thermocouples, then you should know where to invest. For example, in stock market, where will you invest? Will you invest in Reliance Industries or will you invest in some other company? So people do, so they do portfolio analysis, portfolio management, fund manager, blah, 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 all that, okay, in finance. Much in the same way, you can work out a heat map and then Jacobian map and then plot it in various colors and then say that the Jacobian is strong here. I want to look at this part very carefully to solve the inverse problem. So I'll also say there's something called computational frugality and experimental frugality, where I'll say that if some other guy who is not smart uses 100 thermocouples, I'll just use 8 or 12 thermocouples. But by solving the Jacobian, I'll head straight to the answer. Is it okay? So this is the use of Jacobian. Now, any doubts so far? Is it fine? Rajesh Akula, I think he's saying attendance. Attendance for Rajesh Akula is at work. Okay, Jacobian. Okay, problem number 14. Consider the problem. This is our problem which we solve the GNA, right? Okay. So, A Okay, consider the problem MCP dt by, consider the problem of heating of a first order system. So all that jazz, all that English, forget it. Consider the problem. Theta is the temperature excess. Two parameters are A and B. That's it. So we are all engineers. So this much is enough. English is only for communicating. So so many words are not required. Okay, this is enough. All right. Once you take it down, somebody should do a thumbs up. Then I'll dictate the last part of the problem. Have you taken this down? Very good. Okay. Formulate the sensitivity problem. Thank you. Formulate the sensitivity problem. Formulate the sensitivity problem for JA and JB. Okay. See, the previous example I just formulated. Some of you may feel that the learning is incomplete. So I thought we'll take a simple problem, formulate the Jacobian problem, sensitivity problem, and solve it. And anyway, the solution also you know. Okay, so that you feel confident that you know what Jacobian is all about. Okay, formulate the sensitivity problem for JA and JB. Formulate the sensitivity problem for JA and JB and solve them. Please go ahead and solve them. And solve them. Okay. For people who are completely struck, who don't know what is going on in the class, very simple. The formula JA means I'm taking d theta by dA. So take the governing equation and do dou by dou A of this. Okay. Do it to the initial condition also. Then it will result in some equation. That is the formulation for JA. Solve it. Over. Now take dou by dou B of this. Take dou by dou B also of the initial condition. Formulate. That is the sensitivity problem for JB. Solve it. Analytically also, you know what is JA and JB. Cross check and be happy. Have the aha moment that using the Jacobian also, you're able to get the same solution as what you would have otherwise got. So this revalidates your learning because we have taken a problem in which it's easy to see what the Jacobian is. By inspection, it is clear to you. So we are taking a circuitous path, formulating the Jacobian and solving it. 10 minutes, please solve it. So I suggest in the interest of time, odd roll numbers can start with JA, even roll numbers can start with JB. And if somebody is ready, you can just tell me how to proceed. Then I will write the solution on the board. Last part would be the same Jacobian. I will tell you using finite difference how you will evaluate numerically. So this class is we would have seen a suite of problems about Jacobian. Okay, so it will be, hopefully it's well understood. Yeah, odd roll numbers will do JA, even roll numbers will do JB. Okay, then we'll mix and match. So first, I've also written the major step. Use this.
I solved for JA
Oh, very good, very good. Who is that?
because
Vikas. What is the plan? You will tell the steps and I'll write on the board, or you will show it, or what is the funda?
I'll tell on the board.
Oh, so you tell me the. Okay, so shall we start doing? Okay, Vikas is helping us. So let us. This one anyway we know. So this is basically a fun problem. So even if you're doing data science, blah blah blah, whatever, try to do the Jacobian using your neural network. That's where you will distinguish yourself from others. If you're able to do the Jacobian with the neural network, you will do some. So they will know that you're not just a data scientist, you're physics based, you can go deeper. Okay. So neural network based evaluation of Jacobian, that is also possible. Vikas, tell me. So dou by dou A of
B d theta by dt.
what is the this is 1 by B, no?
Sir, no, it is B.
B. Yeah.
So B was MCP by HA, so we divided the whole equation by.
MCP by HA is B. Yeah.
Yes, sir.
No, wait. 1 minus e to the power of minus bt. Huh? Tau equal to 1 by b. Correct? Tau is equal to MC. That doesn't matter. Okay. Okay, that doesn't matter. So we have said MCP by HA is B. Yeah?
Yes.
That cannot be, no? It should be HA by MCP, is it? Anand, what did you do?
MCP by HA only, sir.
But that is B, yeah? Then,
Yes, sir.
okay. No, but that's not what we get in the solution, right?
Tau is equal to MCP by HA only, sir. Because HAT upon rho sub PV. So
No.
Yes,
E
sir.
to the power of theta equal to
So it should when we are using A and B, I think it should not be Q by HA, rather it should be Q by MCP.
no. Q by HA is okay, no?
Yes, sir. We divide and we get.
Yeah. Q by HA is all right. That's not a problem because Q by HA is a steady state solution. I'm worried about the B.
B is basically tau, no, sir. MCP by HA. Tau.
See, B cannot be tau, Anand,
Okay.
because e to the power of minus bt means if this is second, this should be
1
1 by
by tau.
second.
1 by tau, yeah.
So B is so somewhere we have made a. So how do we proceed now? We have to resolve this jam. Okay. How do you do that? Okay. Now let us write the equation in terms of. Okay. Let me get back to the basics. So MCP d theta by d tau. Okay, Vikas, you are there, right?
Yes.
Vikas.
Yes, sir.
Okay. So let us divide by HA. Okay. So MCP by HA
Is B.
B, yeah. So okay, sorry, 1 by B. Okay, 1 by B d theta by d tau equal to A minus theta. Okay, so please take it. Anand, correct yourself. Okay, so sorry, class, please note down that this is the way we have to do. At t equal to 0, theta equal to 0. Okay, now dou by dou A of this. Equal to, correct?
Yes, sir.
Okay. So what is the left hand side? So dou by dou A means 1 by B can be taken out. And so this is dja by, correct? Is it correct?
Yes.
Yes, sir. Yes, sir.
Very good. Okay. So this leads to j equal to 0. Okay. Now just do this. Is there a minus somewhere? No problem. bt, right? So 0 to t. Okay. So all right. So what is this? Minus ln of ga? Huh? Is this correct?
Yes, sir.
J J is 1 minus e to the power of minus b. Okay, I think the beauty is, okay, theta equal to a into 1 minus e to the power of minus bt. That is a solution. Okay, dou theta by dou a is ja equals 1 minus e to the power of. Okay. This confirm. Is it okay? So this is what my Jacobian gives. Anand, very good. Okay, yes, he says yes. So this is what my Jacobian gives. But if I solve it, which we have done it, we have already done it in the class. If you solve it, the original differential equation gives this. Take dou theta by dou a. This actually gives 1 minus e to the power of minus b. Therefore, today we not only composed a sensitivity problem, we solved it. We also got convinced that that answer is indeed right. Okay. So this is the Jacobian. Of course, it is a silly example. This is my own example because you won't find it in any textbook, right? So that a to the power of 1 minus is our own construction, our own construct. But anyway, it's a nice example. Now you know how to get this. So please proceed for B. Please proceed for B is a little bit involved. Okay, Anand, did you revise it? Made it 1 by B?
Yes,
Did you make
no, sir. I was just doing that. I
revise? Any doubts so far? Can anybody confirm? Raja Sundaram, can you confirm that you understood what is going on?
Yes, sir.
Okay, very good. So this is all some little bit high level, but it's okay. You will be able to follow. You're all good in maths. Huh? But this is fun. Jacobian is fun. Okay. Now, for JB. For JB. Okay, dou by dou B. 1 by B. D theta by d tau equals dou by dou B A minus theta minus 1 by B square d theta by dt plus 1 by B Is this correct?
yes, sir.
So d jb by dt plus, so do into b throughout. Okay, so this is the sensitivity problem for JB. So far we have done sensitivity problem for GA, we solved it. Sensitivity problem for B, we have composed, we have constructed it, solve it. Now solve it. We know that theta equal to, but this is some cheating, but we know that theta equal to, therefore d theta by d tau is AB. Okay. This is not so clean because we are getting the solution and then using it. Okay. So you can multiply e to the power of bt throughout. Multiply the e to the power of bt throughout. So some integrating factor, something will come. No? That's it. Integrate. When you integrate, you will get initial condition. Then at time, corresponding time t equal to 0, the JB has to be 0. Therefore, the initial condition will be taken care of. And this again we confirm. We know that A into 1 minus e to the power of minus bt. If we take dou theta by dou A, which is equal to JB, that's again AT e to the power of minus bt. So some basic first order differential equation, some mathematics. So is that okay? Is this fine? Okay, Palash says aerospace guy. Okay, Subha. So it's some fun. Okay, so Manthan, Anand, Subhas, thank you. Okay. Now, so today's class we made a lot of progress. I introduced what the Jacobian is. We did a composition construction of a Jacobian for an unsteady heat conduction problem. We didn't solve it. Then we took a simple unsteady lumped capacitance problem with heating. We composed for JA, JB two parameters and solved it. And it is confirmed that they are indeed the correct values of JA, JB. All right. So we came this far. Then, so please note, the lecture started out with ways and means of calculating Z. I said composing the sensitivity problem and solving it. I showed it to you. Okay. Now, then analytically, that also, you know, analytically is the second part of this. Okay. When you know the solution, get the derivatives with respect to A and B, that is the analytical solution. The roundabout way is composing for the J and JA, JB and solving. That also I have done. The last 7 minutes I'm going to teach you is how to get it numerically. Okay. Same problem. We'll stick with the same problem. Okay. Using finite differences. Okay. Using finite differences. So let's say, what was the GNA problem? Revisit problem number 11, that one. Huh? Please tell me the problem number for the GNA.
10th.
10, sir.
10th problem. Revisit problem 10. Okay. So A is 35. B equal to 0.004. Okay. Now, dou theta by dou A equal to theta at any time A, B reference minus theta T, A reference, B reference divided by A minus A reference. Are you getting the point? You know what I'm doing? Are you able to figure out what I'm doing?
Finite difference.
Finite difference. So what I'm saying is, I'll keep everything the same. At that particular time, for the same B, I will change the A slightly and evaluate the first column of the Jacobian. Okay. So please do that. Please do that. So this A reference will become 35. A is becoming 35.1. Now, so you have to get now using this, you can get all the 6 elements. Analytically, we have calculated the Z. Okay, just look at the first column. Once you understand how you get the first column, then you will be able to calculate the second column. Can somebody proceed? Odd roll numbers, please evaluate the first column. Even roll numbers, evaluate the second column. So for the other one, please take B is 0.0039 second. So if you put up B, you can get this column. If you put up A, you can get this column. That's it. Please give a thumbs up if you are able to follow what I am saying. You may or may not get the solution now. I want a confirmation that you know that we are both talking in the same language. Okay. Manjunath, can you confirm? Pratyusha, very good. Varshi, Tamaya, Pranay, I should see more hands going up. Okay, don't get tired of this Zoom. Till Corona is there, Zoom will be there. Okay. Yesterday I renewed my Zoom. I have a Zoom professional account. Those fellows are commercial guys, right? They said, Balaji, you are a very loyal Zoomer. So I'll give you 20% discount. Extend your Zoom for 1 more year. So I paid 120. I paid $120 on my credit card. I have Zoom for 1 more year. Okay. I don't want Zoom classes to continue, but I have renewed my subscription anyway. All right. So let us do this. Somebody can do the first column. Work out the new temperatures for a slightly perturbed value of A. And then take the difference and do this. You can get the, similarly, at least tell me the first entry. So who is doing that?
0.039.
So who is that? Subhash.
Yes, sir.
What is the first time? Theta time 10 seconds. What is that?
Yes.
10.
Yes.
10 second. 35.004.
35.1.
No, original.
Oh.
How much is that? From the model.
1.3724.
1.37. 10 second. 35.1. 0.004. How much is this?
1.376.
How much is this?
0.04.
04. Okay. So the first one is 0.04. I think we got it as 0392, right? Previously.
Yes, sir.
Okay. So now any even roll number, can you get the first entry here? Yeah, I want some thumbs to go up. I want confirmation that you know what is going on. Is that okay? You know how to calculate the Jacobian now? Finite difference? Hello? Hey, did you followed this or? Very good. Subhash followed. Then Subhash is anyway following. Anybody else? Raja Sundaram? Followed? Okay, Pratiksha, Arvind Raghav, Anirudh. Anand, thank you. So Rishabh, okay. Okay. Now, those data science guys, okay, or those people who are all machine learning types. So if there is a neural network, it will give a lot of input, there is an output. So of all the inputs, you just change only one input. Okay, find out the new output, take the difference between two and divide it by the delta A or delta B, you will get. So using neural network also, you can calculate the Jacobian. So please note that always we need not struggle method of separation of variables, blah, 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 integrating factor and all that. That is, for some problems you can do that. For some problems you can do this. For some problems you can develop a neural network. Okay, you can have advanced finite difference formula for the first derivative and all that. Okay, based on 3-4 points. So you evaluate theta at 3-4 values of A, and then look at the central difference, higher order polynomial, higher order finite difference, whatever you want. You develop a neural network. Okay, whatever it is, you compose and solve it for J. Once you get J, you develop a heat map and find out where J is critical. Those are the regions where you have to pay attention to. Okay. For example, if there is a 1 credit lab and there's a 10 credit or a 2 credit lab and a 15 credit course, you have to spend more time on the 15 credit course. Not that you should not concentrate on the 2 credit lab, whatever, you will concentrate, but you will spend more time on this. It is like this. So, shall we call it a day? So, I have to attend some wedding. Now I have to wear mask and all that. When profs, civil engineering profs' son is getting married. I have to go there now. Okay, Anand to everyone, 30. Yeah. What is that, Anand?
Sir, second entry, sir.
30. What was the thing we got in the class? Huh? 336. Nani Setti.
Yes, sir. 336.44.
300. Yeah,
36, sir.
yeah, sorry.
336. So this is close to what we got now. What we got? This.
Yes.
336.27.
So now you are convinced. So Jacobian. What all magic can we do with Jacobian? I can keep on teaching, but we have to go to Bayesian. So I have that adjoint method, which mathematicians have a great liking for. I will quickly tell you the adjoint method in the Monday's class. That is on 6th. And then we'll go to the Bayesian methods, last 3 classes. Thank you. So have a nice day. So we are meeting after 10 days. Thank you.